Hi, this is Miss Varka. I am going to talk with you now about 13.3, which is the concept of the nature of solids. I'll be going through some different ideas and concepts, including melting point, freezing point, crystalline solids versus amorphous solids, and also the idea of allotropes. And I'll have some examples of those for you. So to start off, let's talk about what a solid is. A solid is a substance whose particles are closely packed together, but also held together so that the particles do not flow. In liquids, we have substances where the particles are fairly close together, like a solid, but the particles can flow. But in solids, the particles can't flow because they're part of either a crystal, or sometimes we have solids that are called amorphous. One thing we do need to understand when we talk about solids is that solid is a state that can be changed based on conditions of temperature and pressure. So, for example, it just happened to have snowed today, so I have some solid water here. So this is water in its crystalline form, and it is crystalline because when it was formed, the temperature was low enough to allow the particles of water to join together into a solid form. Now, since this is now inside my house, it's starting to melt, and we're getting some liquid water as well. And the liquid water is also fairly closely packed together and is able to flow, whereas the solid is in crystalline form. I want to give you an example of a diagram that shows a crystalline form of a solid. So, for example, here is a format, and you can see that when a solid is in crystalline form, it tends to be very regularly bonded with, in this case, intermolecular forces of attraction like water, and that it has a repeating pattern, a geometric repeating pattern. Let's talk a second about melting point and freezing point. For melting point, that's a temperature at which a substance changes from a solid to a liquid. And the freezing point is also a temperature at which a liquid changes to a solid. For the same substance, the melting point and freezing point will be the same value. So, for example, for the substance water, the melting point is 0 degrees Celsius, and it's also 32 degrees Fahrenheit. The freezing point is the same temperature. It is that transition from one state to another, from the liquid state to the solid state. If we had, for example, a substance like sodium chloride, this is sodium chloride crystals, large crystals, it will have a different freezing point, melting point, same thing, and the temperature at which this solid substance changes to a liquid is going to be very specific to this and probably in the 800 plus degrees Celsius. So this is a different temperature for melting point for every different substance. Next, let's look at the idea of a crystal, and I do have some examples of crystals for you. The shape of a crystal, for example, these pieces of rock salt that I have in this container, they reflect the arrangement of the particles within the solid. So sodium chloride does form a crystalline solid. We also have examples where we can have different types of solids that we call amorphous. So if you're looking at the second page of the 13.3 notes, we have an example and some class notes where amorphous solids are solids that do not have a regular crystal repeating pattern. So, for example, if this is compared to this regular crystal repeating pattern, this is a crystalline solid, the amorphous particle diagram you can see is going to be much less regular. So it doesn't have that same repeating geometric array. Here's another way to consider that. If we look at that piece that I had earlier, on this side, we have the kind of irregular array as compared to this crystalline repeating pattern. So this irregular array, that would be an example of an amorphous type of solid. And the best example for that is glass. So the glass for this salt grinder is amorphous solid. So it does not have a repeating array, whereas the crystals inside that are sodium chloride have a repeating array. So the type of solid that glass is, this is class notes, is an amorphous solid. The last thing I want to talk about is allotropes. Allotropes are when we have two or more different molecular forms of the same element in the same physical state. So an example of that would be oxygen in its O2 form, which is gaseous, and its O3 form, ozone, which is also gaseous, but they have different properties and would that even though they're both pure oxygen, just oxygen, they are different allotropes, oxygen gas and ozone gas. Another example of an allotrope is the allotropes that exist for carbon. Carbon can bond in different ways, and I'll show you some diagrams of different bonding for carbon. The first one over here is the allotrope of carbon that is graphite. You can see that we have carbon atoms that are bonded into sheets, and then these lines in between are meant to show intermolecular or interparticle forces of attraction. That is graphite, like we would have in pencils. So here is pencil graphite. We call it pencil lead, even though it's not lead. That would be this form of carbon. The next is diamond, and the diamond form here is every carbon that is bonded to 4 other carbons, so that tetrahedral structure. And to give examples of that, I have a diamond ring on, I have a diamond necklace on. Those diamonds, those are very different form. It's an allotrope, still all carbon, but it is in a different form. Okay. The last one, the one I have here that's shown that looks kind of like a soccer ball, is another allotrope of carbon that's called fullerene or Buckminster fullerene C60. And that, again, pure carbon, but in a different form. Okay, so we have the 3 different forms of carbon: graphite, diamond, and Buckminster fullerene or C60 or fullerene. Those are allotropes. They're all pure carbon, but carbon that is bonded in different ways, so has different types of properties and characteristics.